Good evening. Today we are going to start a new chapter in our second textbook, Mechanical Properties of Solids. In rotational motion, we studied about rigid bodies, if you remember. A rigid body is generally a body that has a definite shape and size, but in reality, you can apply deforming forces to change the shape and size of a rigid body. For example, suppose I have a spring like this. I can apply force so that it gets compressed, thereby changing its shape and size. But if I remove the deforming force, it comes back to its original shape and size. Similarly, I can pull it out by applying a force, but the moment I remove the force, it comes back to its original length and shape and size. And such bodies are what you call as elastic bodies, and this property is what you call as elasticity. On the other hand, if you take, let's say, putty or clay and you apply a deforming force, then you know that it will change its shape and size. And even if you remove the deforming forces, it does not regain its original conditions or original size and shape. And such bodies are what you call as plastic bodies. And this property is what you call as plasticity. Now, in design engineering, or like if you're getting into construction, this knowledge of elastic behavior of materials plays a very important role. For example, suppose you're building a house, you know that there's a heavy load that the concrete and the steel has to support. So if you load it beyond the elastic limit of a structure, if it takes too much load, that if it goes beyond the elastic region of this material, then what happens is the structure won't hold. It'll just go into plastic region and the material will start to flow. And therefore, this branch of physics which deals with the elastic behavior of materials is a very important branch. Today we're going to look into the elastic behavior of some of the materials. Now, what I've drawn here are some figures. So before we go into this, let us talk about the stress that we apply to a body. Whenever we apply a deforming force, like in this case I showed you, when we apply a force to change its shape or size, there will be a restoring force developed in the body which helps it to regain its shape and size. That force is what you call as the restoring force. And the restoring force is always equal in magnitude to the deforming force. It's also opposite in direction. This restoring force per unit area is what you call as stress. So if you look at this, it's the same as pressure. So it's got an SI unit that is Newton per meter square, and its dimension formula is ml raised to minus 1 t raised to minus 2, which you have already learned. So this is called stress, and whenever you apply stress, there will be a strain, which we are going to discuss now. Now, if you look at this first case, we see a cylinder of original length L, and because of the application of a force, we have stretched it to a new length L plus delta L. That means there is a change in length delta L. So, such a stress is what you call as tensile stress, that is, you are stretching it in order to increase its length. You could have also applied a force in such a manner that it decreases its length or compresses it. Such a stress is what you call as the compressive stress. And together, these two are known as longitudinal stress, which is given by the formula F by A, which we know has a SI unit, Newton per meter square. Now, when you apply a longitudinal stress, this body undergoes a change in length. The change in length is delta L, either an increase or a decrease. The ratio of that change in length by original length is what you call as the longitudinal strain. Longitudinal strain. Now, obviously, this doesn't have a unit because it's a ratio between two same physical quantities, delta L by L. So that's the first case where we have longitudinal stress producing a longitudinal strain. In the next case, you will see we have a cylinder here of original length L, but we have applied a force here to the upper face pulling it to the right and a force here to the lower face pulling it to the left, such that the upper face is displaced by a distance delta x or an angle theta. Now in this case, the stress is called as the shearing stress or sometimes also referred to as the tangential stress. Tangential stress, which again is F by A, and because of this there is a strain called as the shear strain, which is given by tan theta approximated to theta for small angles. Tan theta is opposite side by adjacent side, so this is delta x by L. So here delta x is the displacement, how much has the upper face been displaced with respect to the lower face, and L is the height of that cylinder, or this is delta x by L is actually tan theta, which is what you call as the shearing strain or simply shear strain. For example, suppose I have a book like this, okay, and you will see now that this is the length or height of this book, and here we have this is perpendicular. If I pull this upper face with a force to the right, you will see that there is it was like this before, so it has been shifted through an angle theta through a distance delta x, and that tan theta is what you call as the shear strain. So that is what we have to discuss in the second case. And here again, delta x by L being a ratio of the same quantities, we don't have a unit, but stress has the unit Newton per meter square. Then we go on to the last one that we have seen here, that is we have pressure being applied, which is changing the volume of the body. So change in volume is delta V, and the original volume we take as capital V. So here this pressure we normally call as a hydraulic pressure, which is again stress. So hydraulic pressure or simply stress is P, and there is a change in volume of the body. So it's called the volume strain given by change in volume by the original volume. Here again, because we have a ratio, we don't have any unit. Pressure has the same unit as Newton per meter square or Pascal. So these are the three different cases that we discussed here. Now from here we move on to Hooke's law. Robert Hooke performed a series of experiments studying the elongation of different kinds of materials, and he put forward his law called the Hooke's law, which says that the stress applied to any body is directly proportional to the strain on the body, or stress is equal to some constant into strain, or this constant, which is called as the modulus of elasticity, is the ratio of stress to strain. This is called the modulus of elasticity. Modulus of elasticity, which will again have a unit the same as stress, Newton per meter square or Pascal, simply because strain doesn't have a unit, but stress is Newton per meter square or Pascal, and therefore the modulus of elasticity also has the same unit. Now this modulus of elasticity is called the Young's modulus if we are talking about longitudinal stress and longitudinal strain. If you are talking about shear stress and shear strain, then the modulus of elasticity is called the shear modulus. And if you are going to talk about hydraulic pressure and change in volume, that is volume strain, then we call that modulus of elasticity as bulk modulus. So let's write down the formulas for that. So we have here the first one, which is Young's modulus. So we have Young's modulus. As you know, Young's modulus Y equal to stress by strain. So in the first case, stress was F by A divided by the strain is delta L by L, or this is F into L by A delta L, where F is the force applied, L is the original length, A is the area of cross section, and delta is the increase in length when a force is applied. And Young's modulus has the same unit, modulus of elasticity, which is Newton per meter square or Pascal. In the second case, we have, we call this as the shear modulus. Shear modulus, denoted by the letter G, which is shear stress by shear strain. Shear stress again F by A, by shear strain is delta X by L, or you may even write it simply as theta. This is FL by A into delta X, where L is the height of this cylinder. Delta X is the displacement of the upper face with respect to the lower face. A is the area of cross section of that cylinder. And the last one is the bulk modulus, where we have the bulk modulus given by the letter B, which is hydraulic pressure, that is P by the strain. Volume strain is delta V by V. So we have delta V by V. We put a negative sign here because you see, in this case, when you increase the pressure, the volume of the body decreases. But if you decrease the pressure, volume of the body will increase. And because of that, we use a negative sign here. So that is minus PV by delta V. The inverse of this is called compressibility. Compressibility, which is K, which is 1 by B, which is minus 1 by P into delta V by V. Gases are highly compressible, solids are the least compressible. So inverse of bulk modulus is compressibility. So these are the three modulus of elasticity that we need to learn. Now, a body has higher elasticity if it has higher Young's modulus. For example, steel is more elastic than rubber because steel has a Young's modulus of 200 gigapascal, whereas rubber has a Young's modulus of 0.001 gigapascal. So it's a very small value. That is simply because this is stress by strain, right? Stress by strain, which this is equal to delta L by L. So if you apply the same force on two rods, one is steel and the other is rubber. So when you apply the same stress, you know that the change in length is, the strain is lesser for steel, for rubber it is more. So elasticity in physics is the ability of a body to resist the change when a deforming force is applied on it. So steel has a higher resistance to change when the same stress is applied compared to rubber, and therefore steel is more elastic than rubber. The last thing that we need to do in this chapter is the experimental study of variation of stress with strain, and that is what we are going to discuss now. Experimental study of variation of stress with strain. So you can actually load, you can take a wire, maybe steel, and start loading it. The force applied here will be the M into G, and so we may calculate the stress by F by A, finding out the area of cross section of this wire that we are using. And as we load it, we can find out the change in length by original length will be what we have as strain. And these two quantities is what we are going to plot on a graph. We are going to plot the strain along the x-axis and the stress along the y-axis. This will be in Newton per meter square. Strain, as you know, has no unit. Now, if you study this, you will see that for some time it's a straight line, and then as a slight curve. The stress strain graph will be different for different materials. Now there's a first region which is O to A, then there's B, this is B, this is point D, and this is point E. So let me draw a dotted line here. Okay. Now, if you look at the first section, O to A, you will see that stress and strain are directly proportional to each other because it's a straight line. This first part is a straight line showing you that stress is directly proportional to strain, which means in that region, the body obeys Hooke's law, which says stress is directly proportional to strain. So that means If you continuously load it, the stress and strain are directly proportional to each other. Not only that, it is in the elastic region. That means, let's say you loaded it and then it increased its length by delta L. If you completely unload it, remove all the load, it will go back to its original length L. So, if it is able to go back to its original length when the complete load is removed, then you know that it is in the elastic region. So, this O to A, two things. One, the body obeys Hooke's law. It's also in the elastic region. But if you look at this point A to B, you will see that this is not a straight line, it's curving. It means that if it's not a straight line, it means that stress is not proportional to strain. And therefore, the body does not obey Hooke's law, but it is still in the elastic region, which means you may continuously load it. The length of the wire will go on increasing. Let's say there is an increase of delta L, but the moment you unload it completely, it will go back to its original length L. So then this A to B, the body is still in the elastic region, which means if you completely unload it, it will go back to its original length. It is not obeying Hooke's law because it's curving. That means stress is not proportional to strain. This maximum limit up to which you can load it so that the body is in the elastic region is what you call as the yield stress. I'll write it out here for you. Yield stress, denoted by SY. So this is the yield stress, which means the maximum limit up to which you can load this material. If you load it beyond that, if you continuously load it beyond this stress value, then the material will go into plastic region, which means if you unload it, it does not come back to its original size and shape. So the elastic behavior of the material is only from O to B. Now after the maximum limit, that is the yield stress, then if you load the wire, you will see that even for small increases in stress, you have a very large increase in strain. That is when you say the material starts to flow, because you are not actually loading it much. You see that the increase in stress is very little, but the increase in strain is large. So the body is now increasing its length even for very small increases in stress, and then the body is said to be in the plastic region. If it is into the plastic region, you can unload it completely, but still the body does not come back to its original length. There will always be a permanent set. That means, let's say at this point C, we completely unload it. We remove the whole stress and we brought the stress back to 0. If it is in the elastic region, the strain would also come back to 0. But you see, now the strain is not back to 0. A permanent set is left in the body, in the material, which is called the permanent set. For example, suppose let's say this was 5 centimeter. You loaded it and it's increased to up to, let's say, 5.9 centimeter. When you completely unload it, if it is in the elastic region, it would come back to 5 centimeter original length. But at a point C like this, where it has entered into the plastic region, even if you remove the load completely, this might go back to, let's say, 5.2 centimeter, which means a 0.2 is remaining as the strain. That is delta L by L is 0.2. So that is what I meant, that there is a permanent set in the material. This point here is called the ultimate stress. Ultimate stress or ultimate yield stress, SU, where if you load it now beyond this, you see now after point D, actually the stress is decreasing. The curve is coming down. That means you're decreasing the stress. You're removing the force. You're removing the load, but the strain is still increasing. So this is the maximum limit beyond which, even if you remove the load, the length of the wire is going to increase. And at some point here, this is called the fracture point. The wire will break, called the fracture point. Point E is called the fracture point. Now, if this D and E are very close to each other, we know that it is a brittle material like glass. But if D and E are very far apart, it means that you can pull this wire to large length without breaking. that is like gold and things like that, which are very ductile, so that you can pull it out into long wires without breaking. So this is a stress strain graph which is studied in 4 regions: O to A, where it obeys Hooke's law and it is in the elastic region; A to B, where it does not obey Hooke's law but it's still in the elastic region; from B to D, it is into the plastic region, where even though the stresses very slight increases in stress produces large increase in strain, and so it's in the plastic region. And even if you completely unload it, it will still have a permanent set. This is the ultimate stress that you can apply, beyond which, even if you decrease the stress, you see that the strain is going on increasing. So this is about all in this chapter, mechanical properties of solids. Thank you.